Hi, everyone. My name's Taylor with the Beta Angel Project, and today I want to share with you some of the more influential research papers that helped me to be able to improve the athletes and their performance over the course of the past decade or so. We're going to be starting with 2018. Why 2018? Well, it's the last time I really updated the Beta Angel Project's research inventory, and so I've started to re-update it. I'll be updating it with 2019, 2020, et cetera, and doing some of these videos as well. So when it comes to what specifically we're looking at, I'm going to highlight the upper right-hand corner of the screen right now. We want to look for protocols to test, measurements to monitor, constraints to manipulate. And by that, I mean things that you can change that will have an impact on the outcome. So where you can change the outcome. And then also shifts in how to interpret athlete response so we can change training decisions. Now, today we're not going to be going over critiques of the methods. We are primarily just looking for ideas, research to practice. We want to see what we can take from these papers that can help directly with athlete training. So first paper I want to go over is the effect of 8 weeks of two different training methods on on-site lead climbing performance by Philip et al. And this paper is not open source. Many of the papers will be, but this one I can show you my website, which has the protocols. And so we'll go to the Beta Angel Project on the left, go up to menu, experimental training, down here to the Austrian protocols. So this was a pretty cool paper because it involved a collaboration between research scientists and Austrian coaches. So I want to, start pretty simple. Keep in mind where I was in 2018. I'm trying to find new ideas to help support the athletes. Athletes love new things, so if you find a new protocol, they'll want to do it. So in this case, I'm just going to contrast two parts of this of the muscular endurance training plan: extensive intervals and intensive intervals. These are climbing focused protocols. Extensive intervals are really simple. One lead route 10 times in a row. You can change the one lead route, and I encourage you to do that because, just doing the same lead route over and over again, not exactly super interesting for most climbers. I want to contrast that with intensive intervals. Two blocks of top rope climbing involving 8 sets of 25 moves. So whereas with extensive intervals, we had this sort of more aerobic base building. With intensive intervals, we have a more anaerobic response, or we're trying to elicit that adaptation. So the things that you can change with respect to this, well, I almost never did two blocks of 8 sets of 25 moves, a little too much. There's so many other things in climbing to train. So let's say you do one block. I typically tended to, I rarely did 8 sets. I became more common for me to do 3 sets, 25 moves. 25 moves, it does not take you to the top of the wall in most climbing gyms. So this is about like 60 to 80% of a wall, and you actually have to come off the wall. And a lot of athletes didn't love that. But at the same time, you're trying to elicit a specific bioenergetic adaptation. And so that's really important. How much rest? Well, down here it basically tells you if it took you a minute to get to hold 25, you rest for 40 seconds, so about 2/3. So you can change all sorts of things, change the rest times. You notice your athlete, or you notice yourself if you're doing it, start to fatigue. Give more rest. If there's not as much fatigue, give less rest. You can change the number of sets. You can change the number of moves. Oftentimes with more elite athletes, I was having them do the lead climb for the first, and then they would top rope on the second, assuming it was a vertical enough wall. One thing to note about this, this is a lot of volume, 10 times in a row, 8 sets of 25 moves. If I gave this to a type A climber, they would pick their favorite route, especially a really good climber, and maybe there's only one 513 in the gym, and they're just like, they're going to try to go up it over and over again. And so what I started to notice was if they hit a tweaky move and they did that over and over again, there might be an issue there. So I would encourage them to kind of go off route, pick a different hold, get them through the tweaky moves so they don't have to deal with that with just that single move, or change the route and in order to keep themselves safe and healthy. Next paper I want to talk about is Determinants of Optimal Leg Use Strategy, Horizontal to Vertical Transition in the Parkour Wall Climb by Croft et al. We just did a sport climbing paper. Now we're going to talk about more of a bouldering-oriented competition paper. So in this case, This paper was not climbing specific, but it does still apply to climbing with run establishes up to the wall, as well as skate style moves across the across volumes as you're doing some sort of coordination or electric move. So if you look down in the lower right, I will call this the mustache strategy. If you look at the line, it kind of reminds me of a mustache. We've got the bridge of the nose here. We got the droopy portion of the mustache on either side, and maybe you got a little flare on the edges if you're using some kind of product. Um, so this always made me laugh thinking about this as a mustache. So the four constraints to manipulate here. Speed is the first one. And then we have the ground contact point before the transition to the wall. So where is the foot just before you leap up onto the wall? Where is the foot when you actually hit the wall? And then how much do you basically load in or drop in horizontally into the wall prior to redirecting force to go vertical. So let's imagine you're trying to change one of the constraints. Let's just go with speed. This was done with an elite parkour runner. He was, I believe, going around 4.7 meters per second. The model that they used to try to optimize his strategy recommended he slow it down to about 4.5 meters per second. So, but you're not going to be able to, you probably won't be able to measure any of those things or think about 4.7 versus 4.5. So just think about upping the speed or lowering the speed. How does that then change your foot location on the ground prior to leaping to the wall? Or what about the leap onto the wall? Or how about how much you actually drive into the wall prior to redirecting the force upwards? So these, I'm not going to tell you how to do this or which constraint exactly to manipulate or what should happen. That's about exploration and experimentation on your own. I just wanted to kind of point this out as a resource. Hey, these are some cool constraints you can manipulate and play with as you learn how to be a better wall runner. Next paper I want to go into is ACTN3 Genotype in Professional Sport Climbers by Ginst et al. This paper was so cool back when I first read it. First genetic study I've ever picked up, and I had a lot of learning to do, a lot of base building. I just didn't know anything about the topic. So let's go ahead and we're not going to go into it super deep. This is going to be like genetics 101, if that. So the actin-3 gene or the ACTN3 gene, this is a gene where, well, in all cases, get one copy of the gene from mom, one copy of the gene from dad, and that copy will either be R or X. And so if you think about it, you basically, since you have two copies, you either are going to have one of three genotypes, RR, RX, or XX. What does R do? Well, this is the active form of the gene versus X, which is the inactive form of the gene. What the active form does is it codes for a protein that helps support your most explosive muscle fibers, your type 2X muscle fibers. And so you can imagine that the RR genotype has been studied in other power sports and has been associated with power athletes, the best power athletes. Does that mean XX is associated with endurance athletes? There's caveats to that, and we're not going to go into that too in depth today. We'll talk a little bit about lead climbers later. Bottom line is you have these three genotypes, and this study had a very cool population of high elite boulderers. So high elite is even more elite than elite. And these boulders are some of the best in the world, and they also had high elite lead climbers as well. So if you take a look at these numbers, it's hard to draw, it's hard not to see that 81% of high elite boulders had the RR genotype. Very much suggestive that that there is a genetic component to being an amazing boulder. I don't want you to focus on that. What I want you to focus on is that almost 1 in 5 of these high elite boulderers did not have that RR genotype. Why is that important? Well, we want to empower ourselves. First off, you're probably not going to go out and get a test, and I don't encourage it. I think most people don't encourage you to figure out whether or not this genotype is whether you have the RR genotype. Um, but we want to be able to see, hey, 19% of these high elite boulders figured out how to find success. How did they do that? Um, so we'll go into that in just a second. But before I do that, I do want to note that there was no, the ACTN3 gene did not appear to have, the genotypes didn't really have high prevalence in sport climbers in terms of RR versus RX versus XX. So it's not necessarily about power, not necessarily about endurance. They found success regardless of their genotype when it comes to the ACTN3 gene. So the next thing I want to point out is I want to point out how we can find success when it comes to things that are a little bit challenging to change. So I'm going to point to a paper called Interindividual Variability in the Adaptive Responses to Endurance and Sprint Interval Training, a randomized crossover study. This is by Bonafiglia et al. It's published back in 2016 in the journal PLOS ONE. Um, we're going to go down to one of my favorite graphs on the face of the planet. Now, the reason why it's one of my favorite graphs is because most research papers, they love p-values and effect sizes. They love uh, uh, means and medians, descriptive statistics and standard deviations. Um, but what they don't tend to do is do a whole lot of reporting on the individual. And so this does. This was a crossover design with a washout. So basically what this means is that you had two groups and they both did both protocols. So in other words, we have the protocols on let's look at the lower graph right now, sit versus end. These are two protocols. And both groups did both protocols. We have so sprint interval training and endurance training. And what they were measuring, lactate threshold. What's the lactate threshold? Well, this is a threshold at which you first start to get pumped. There's another threshold later on called the onset of blood lactate accumulation, which is when you start to get quite a bit more pumped. But lactate threshold is where you first start to get pumped. So if you can imagine, if you can push that back a little bit, it'd be helpful for climbing. Now, this was not a climbing-oriented paper, so I'm going to translate this over onto climbing. What were the protocols? Well, sprint interval training, this is 20 seconds on, 10 seconds off, so kind of like a long boulder problem. It's moderate to intense climbing, and then some number of repetitions of that 20 seconds on, 10 seconds off. And then with the endurance training, that's like 20 to 30 minutes on where you up and down climb, traverse, that sort of thing. Um, what are we looking at? Well, if we look at the individual dots, you can see that there are essentially four categories. You had people who responded to both in this category up here, to both protocols. You had people who responded to neither protocols here. Then you had people who responded to one, but not the other. So in this case, this individual responded really well to sprint interval training, but did not respond to endurance. And likewise, these individuals over here responded really well to to endurance protocols, but not to sprint interval training. And then you had individuals like down here who responded to endurance, but they actually had an adverse effect associated with sprint interval training, which is unfortunate, but it happens. It's important to note that across this study, everybody responded to something, and I think that's the empowering note to take. Is let's imagine lactate threshold says force. Let's imagine, and so we're measuring force, and because you want to improve your force. And now you are working in with a friend of yours, and that friend of yours starts doing plate pickups with a 20 millimeter edge, and it's a 3 seconds on, maximum pull at with 3 minutes of rest with some number of sets. And you guys are going through this week after week, and you get to week 5 or 6, and you're noticing your gains just aren't there, not compared to your friend. And this is kind of, it's a little demoralizing. Definitely, your friend is a super responder; they're gaining so much finger strength. Change the protocol. So we can imagine that, let's say instead of end down here, you have 7 seconds on, 3 seconds off for, let's say 6 or 7 repetitions. You can start to push the repetitions up as you progress with a 1 minute rest in between. Um, and you can also push the sets, of course. Now, this is a different type of protocol that has shown increases in force in the past. So you could use this protocol, and you might respond better to this protocol as opposed to your friend's protocol. To me, this is, we don't know why you're not responding to the other protocol. Could be genetics. Could be nutrition, could be sleep, could be any one of a number of factors. The point is if you don't see the response, change the protocol. So those are the three papers and ideas I wanted to go over. As you can tell, I'm very interested in changing things and going from research into practice. I'll have a few more papers coming up soon. Thanks for coming and watching. Appreciate it.